This is a fully 3D printed drone that I designed from scratch, and as fun as this project has been, it definitely had its ups and its downs. In this video, I'll walk you through the full design and build process so you can make one for yourself. I designed everything in SolidWorks, focusing on using as little hardware as possible while keeping it easy to assemble and repair. Here's a quick time lapse of the 30+ hour designing process. It's also worth mentioning that this wasn't my first prototype. I went through several earlier versions that I scrapped due to strength and stability issues. The design is split into four main components. First is the hub, which everything else attaches to. I didn't compromise on its strength, since it takes on about 90% of the drone's stress and vibrations. Next is the TPU bottom brace. It holds and protects the battery from below while absorbing impacts from crashes and hard landings. This part needs to be printed in TPU so you're not reprinting it every other flight. Then there's the top cover. While it isn't necessary for performance, it protects your electrical component from water, snow, and dirt, while also shielding them from impacts. And finally, there's the four arms. These slot securely into the main hub without the need for any hardware. The tolerances were carefully designed to ensure they're not too tight or loose. Now, if you're interested in making this drone but don't have access to a 3D printer, then you can use a sponsor of this video, PCBWay. They offer an easy-to-use and affordable 3D printing service. You can print all the components for this drone using PETG, like I did originally, or you can use nylon for additional strength. I had the main hub and arms printed in nylon and they turned out great. The clearances are down to the millimeter, and the surface finish is really nice. Use the link in the description to order some parts with a discount. Here's a quick video of how to assemble everything. Before installing the props, calibrate and configure everything in Betaflight. This is safer and helps you identify which props go where. I'll cover the configuration next. The calibration process took me much longer than I expected, mainly because this was my first time building a drone. I went through multiple tutorials and documents before I could get it flying, and I highly recommend you do the same to avoid damaging your drone, and possibly saving your fingers too. Here are some of the main things you'll want to check. Make sure your accelerometer is calibrated and that the front of your drone matches the orientation in the 3D simulation. You'll also need to configure the motor directions, with the props removed of course. I had to manually rewire 2 of the motors because my ESCs wouldn't switch directions for some reason. You should also bind your transmitter and receiver and set up arming switches. If you're not using FPV, make sure your drone is set to angle mode. I also found enabling head-free mode useful. There may be other steps I've missed, so I recommend watching a few YouTube videos to make sure you've covered everything. Now you should probably be careful when doing this, but make sure that when you turn your drone in one direction, it tries to push it in the opposite. That will tell you that your gyroscope is working properly. Here are some of the previous prototype designs. As usual, all the files for this project are available on my GitHub and MakerWorld profiles for free. If you have any questions or concerns while building, you can contact me via Discord, Gmail, or Instagram. In this first test, my motor directions were incorrect, which caused the drone to go crazy. Thank God I had it strapped down. After I fixed that, my drone wouldn't launch. I later found out that it was due to me flashing the incorrect firmware. Although even after fixing all those issues, I still wasn't the best pilot.
Oh, shoot. Oh my God.
I then had the brilliant idea to fly it outside at midnight. I think you can guess what happened next. I lost sight of it and it ended up crashing into a tall tree. The drone is all the way up there. You can barely hear it. You can actually hear it pretty loud. I got this ladder in the middle of nowhere. And a stick. God knows if I'm gonna be able to get it from there, man. Thankfully, after several hours of trying, we finally got it back. The only real damage was a broken arm and a wire that got detached from the motor windings. Despite all those failures, I eventually managed to get the drone under control and capture some pretty decent footage. In theory, this drone should be capable of reaching speeds of up to 200 km per hour, although I don't have a GPS yet to confirm that. In my latest design, the drone is around 650 grams, reaching up to 750 with a camera on it. With the 6S LiPo, I can easily get 10 minutes of flight time. Trying to drive the drone close to the ground in this clip. However, I got too close and forgot to shoot up. Here's some quick legal information for you. If you're in Canada, there's a few laws and regulations you should be aware of. First, you must register your drone with Transport Canada, since this design weighs more than 250 grams. You will also need a basic flying certificate if you plan to fly in open areas away from people. I went ahead and got the advanced certificate as well, since it offers more flexibility and additional privileges. Wherever you live, make sure to check your local rules and regulations before flying. Now, although this project was quite a success, I'm not planning on stopping anytime soon. I've been researching Mavlink and ArduPilot Mission Planner to be able to use and map the GPS location of the drone real time. And the main reason for this is to be able to run autonomous flights. This will all be done via the telemetry on the transmitter, which will get GPS coordinates through the ELRS receiver and forward it to Mission Planner. Although for that I'm going to need a more advanced transmitter, something like the Radio Master Pocket Crush, because the current one I have, the Radio Master T8L, does not support this use. Once I've figured that out, I'm going to integrate LiDAR sensors, RGB cameras, barometers, and a magnetometer to integrate object detection and tracking. This is all part of my goal to make this drone fully autonomous for various different uses. The biggest issue will probably be funding, as some of these components cost more than the drone itself. For the rest, there's thankfully tons of information documented by various users on GitHub. Anyways, that's enough for this video. If you'd like to see more of this project, let me know in the comments and subscribe to stay tuned for updates.